Some procedures I will speak now. Maybe helpful somewhere. Energy stored in a capacitor. When a capacitor is charged, in the sense, initially when we take a capacitor, there will be no charge on the plates. If we transfer the charge, transfer electrons from one conductor of this capacitor to the other, one conductor starts getting positive charge and other conductor starts getting equal amount of negative charge. Now, once a capacitor, in general, I will just talk about a parallel plate capacitor only, is charged like this, and the capacitor is open circuited. Earlier, I would have connected an agent, a source of EMF, a voltage source I would have connected to charge it. The charge on the plates of the capacitor is Q, and the potential difference between the plates of this capacitor is V. Maybe if it is charged by using a DC voltage source of voltage V, at steady state, this is the case. We are going to see it in transients. Now, having charged, if you connect a bulb or a resistor between these two terminals, current flows through that resistance. That means a charged capacitor is capable of circulating current through a resistor, means it is capable of doing electrical work. It got this ability because it contains energy. Energy gets stored. A capacitor of capacitance C is charged to a potential difference of V. Means what? There will be a charge Q, plus Q on one plate and minus Q on the other plate, equal to CV. I say that energy is stored in the capacitor. Whenever I say that energy is stored in the capacitor, we should know that it is getting stored in the dielectric part of the capacitor. It is getting stored in the dielectric part of the capacitor. Because we saw in the topic potential only. That's why I spoke about that there. When we deform any elastic object, I told you that potential energy gets stored. I took the case of spring. It is true for any elastic object. If you deform it, which we have to apply the force to deform it, at each and every extent of the course of deformation, from one state to the other state, the elastic member exerts restoring force opposite to the applied agent force. Restoring force. And you have to work against that restoring force to deform it. When I say that energy is stored in a capacitor, it is stored in the dielectric part. This dielectric definitely consists of atoms. And we know very well that atom is considered to be a spherical object. with positive charge concentrated at the center called as nucleus, and negative charge in the form of electron cloud moving around the nucleus. When you basically talk about an atom, if it is not there in the electric field, the positive charge center coincides with the negative charge center. Positive charge center coincides with the negative charge center. But when it is kept in the field in this particular direction, if there is field, what will happen? Positive charge moves in the direction of the field, and negative charge moves in the direction opposite to the field, because field lines are drawn with taking the force direction, the force experienced by the positive charge. Earlier, as I showed, right, this is the negative charge, this is the positive charge. Once it is kept in the field, naturally positive charge moves to the right, and the negative charge cloud will deform, taking the center to the left. No, it is in a deformed position. Once you remove the field, it regains its original shape. You agree with this? So, every atom that is present in the dielectric region will be there in the deformed state when there is electric field between the plates of the capacitor in the particular region. So energy gets stored in the dielectric region. Now there is a specific requirement for us, because of which I am doing it. Now, what is this total energy stored in the capacitor of capacitance C, charge to a potential V, or charge so that the charge on the plates is Q? Because these three variables, now Q, C, V, are related through an equation. If you know two, the other thing is known to me. If, listen carefully, any capacitor is charged with Q coulombs of charge so that the potential difference between the plates of it is V, the energy stored in the capacitor E is equal to E is equal to, if you know, tell me, what is the energy stored in the capacitor? Half QV. This is what we derive also. We know again very well that this is the potential energy. And at least now you will understand the significance of what we had at the discussion in the beginning of potential. Potential energy is always equal to the work done against an opposing force. Potential energy is always equal to the work done against an opposing force. If there is no opposition, there will be no potential energy, because it need not do any work. Now, we know that when you have two conductors just separated by a dielectric, there will be no charge on it. The potential difference between these two conductors, if there is no charge, is zero. If we transfer an electron from one conductor to the other conductor. One becomes plus, another becomes minus. Excuse me. If you want to transfer one more electron from positive to negative plate, this fellow positively charged plate attracts it. And if I want to put it in the negatively charged plate, it repels it. Every next electron is to be transferred opposing the attractive force from the positively charged conductor and the repulsive force from the negatively charged conductor. Let us suppose when one electron is transferred, small v will be the potential difference. For the next electron to be transferred, for the initial electron to be transferred, I'll say there is no work done. Only one work is done against the attractive force from the positively charged object. Once I remove the electron, it becomes positive. As long as I take it to the negative another plate, it will be attracting it, but I'll take it against it and then put it in the negative charge. Once I put it in the negative charge, they attract each other and they remain there. Now I have to do VE amount of Q, because I told you, right? That's why I told you, if there is a potential difference of V volts between 2 points, to transfer a charge from one point to the other point against the field force is QV joules. Small v potential difference has come. One electron I will transfer against it by doing work equal to VE. Now the potential becomes 2V. The work done will be 2VE next to transfer the next electron. Once I transfer the next electron, it will be 3V. If I transfer the electron doing the work of 3VE, it will be 4V. Like this, I have to continuously transfer the electrons against increasing opposing force. This is now taken as, of course, this is how it is to be studied. There is nothing like tending to zero dq charge for me practically. Charge is always quantized with respect to the charge of electron is what I showed. If ultimately that capital Q is so many n times, check it carefully. I will now look at the work. First electron, I will consider no work is done because there is no potential difference initially. For the next electron to transfer, VE joules of work is done. Now 2V is the potential difference. 2VE is the work done. Next 3. 3VE is the work done. Next 4. Like that, I will increase. Because there is nothing like tending to zero impact, but we can use that also. I will show it. Listen carefully. Total number of electrons transferred is Ne is Q. And the potential to which it has risen is N small v due to each electrons transfer. Enter this. At each stage, this area is the work done. Together it is what actually? I will adjust it to be a triangle, right? I think you understood this point, right? I will do this so that this half I'll fill it here. This region is kept here so that it becomes a triangle of height NV and charge NE. This is capital V, this is capital Q. What is the area of this triangle of height V and width base Q? Half QV. Whichever the way you understand. Listen carefully. Intermediate voltage integral of small v dq. what I can derive? Integral small v dq. Let us say from 0 to capital V. I know that at every position q is equal to cv, dq is equal to cdv, because of which this will become 0 to v small v cdv is what? Half cv squared is what I can derive, or v is equal to q by c. I can substitute small v is equal to small q by c, making the integral as small q by c dq from 0 to capital Q. Capital Q is equal to C capital V. This will become Q squared by 2C. But actually it is half QV for them. It will give, since Q is equal to CV, C is equal to Q by V, half of Q by V into V squared is half QV. I have three different formulae, and we should know all the three formulae. It can be half CV squared or Q squared by half Q squared by C or half QV. Where capital C is the capacitance of the capacitor. V is the ultimate voltage across it when it is charged, and capital Q is the ultimate charge on the plates of the capacitor. It is universal statement, irrespective of whether it is parallel plate capacitor, cylindrical capacitor, single dielectric, mini dielectrics, spherical capacitor, whatever it is. I just took the relation between the variables. Definitely when it is getting charged, that's why I did not take a parallel plate, no arbitrary shaped conductors. They will continuously charge the electrons against the increasing force of opposition. And whenever there is a potential difference of V volts between the plates, to transfer the next electron, EV joules of work is to be done. QV I told there. Q is E now, because I'm transferring electrons from one conductor to the other conductor to charge them with opposite charges.